Hello everyone, welcome to this course, Organic Spectroscopic Analysis. In previous class, I have introduced you the UV spectroscopy, and in this lecture, we will learn the instrument and the spectrum character of UV. The construction of a traditional UV visible spectrometer is very similar to an infrared instrument, as similar functions, sample handling, irradiation, detection, and output are required. Here is a simple schematic that covers most modern UV spectrometers. Two sources are required to scan the entire UV visible band. Deuterium lamp, which covers the UV from 200 to 330 nanometers. Tungsten lamp covers from 330 to 700 nanometers. The lamp illuminates the entire band of UV or visible light. The monochromator grating or prism gradually changes the small bands of radiation sent to the beam splitter. The beam splitter sends a separate band to a cell containing the sample solution and a reference solution. The detector measures the differences between transmitted light through the sample versus the incident light and sends this information to the recorder. As each band is to be measured separately, time is required to cover the entire UV visible band due to the mechanism of changing wavelengths. A recent improvement is a diode array spectrophotometer. Here, a prism dispersion device breaks apart to full spectrum transmitted through the sample. Each individual band of UV is detected by an individual diode on a silicon wafer simultaneously, and the obvious limitation is the size of the diode, so some loss of resolution over traditional instruments is observed. Virtually all UV spectra are recorded in solution phase. Cells can be made of plastic, glass, or quartz. Only quartz is transparent in the full 200 to 700 nanometer range. Plastic and glass are only suitable for visible spectra. Concentration we will cover shortly is empirically determined. A typical sample cell, commonly called cuvette. Solvent must be transparent in the region to be observed, and the wavelength while a solvent is no longer transparent is referred to as the cutoff. Since spectra are only obtained up to 200 nanometers, solvent typically only need to lack conjugated pi systems or carbonyls. Common solvents and cutoffs are shown here. Then let's look at how UV spectroscopy used for structure determination, although it's very rare to only UV spectrum to determine structure of a molecule, more likely coupled with other spectrometric techniques such as MS, NMR, infrared, which we have learned in this class. For acyclic butane dyeing, two conformers are possible, the S-cis and S-trans. The S-cis conformer is at an overall higher potential energy than the S-trans. Therefore, the homoelectrons of the conjugated system have less a jump to the LUMR lower energy with longer wavelengths. Two possible pi to pi star transitions can occur for butane dyeing, phi 2 to pi 3 star and phi 2 to phi 4 star. The phi 2 to phi 4 star transition is not typically observed. The energy of this transition is outside the region typically observed, which is 175 nanometers. For the more favorable S-trans conformation, this transition is forbidden. The phi 2 to phi 3 star transition is observed as an intense absorption. The phi-2 to phi-3 star transition is observed as an intense absorption. Epsilon is equal to 20,000, based at 217 nanometers within the observed region of the UV. While this band is insensitive to solvent, as would be expected, it's subjected to the basochromic and hyperchromic effects of alkyl substituents, as well as further conjugation. Woodward and Fishers performed extensive studies of terpene and stearidyl alkenes and noted that similar substituents and structure features would predictably lead to an empirical prediction of the wavelengths for the lowest energy pi to pi star electron transition. This work was distilled by Scott in 1964 into an extensive treatise on the Woodward-Fisher rules in combination with comprehensive tables and examples. A more modern interpretation was compiled by Rao in 1975. The rules begin with a base value for lambda maximum of chlorophyll being observed as a cyclic butadiene, which is 214 nanometers. The incremental contributions of the substituents is added to this base value from the group tables here. As Woodward-Fisher rules for the cyclic dienes, there are two major types of cyclic dienes with two different base values. That is the trisoid and cis-soid. The increment table is the same as for acyclic butadienes with a couple additions. In the pre-NMR era of organic spectral determination, the power of the method for discerning isomers is readily apparent. Let's see the UV spectra for enols. For oxochromic substitution on the carbonyl, pronounced hypoxochromic strips are observed for the N to pi star transition. This is explained by the inductive withdrawal of electrons by oxygen, nitrogen, or halogen from the carbonyl carbon. This causes the N electrons on the carbonyl oxygen to be held more firmly. It's important to note that this is different from the oxochromic effect on P to P star, which extends conjugation and causes a basochromic shift, which is redshift. In most cases, this basochromic shift is not enough to bring the P to P star transition into observed range. General features, conversely, if the carbonyl system is conjugated, both the N to pi star and pi to pi star bands are basochromically shifted, which is redshift. Here, several effects must be noted. First, the effect is more pronounced for pi to pi star transition. If the conjugated chain is long enough, the much higher intensity for pi to pi star transition band will overlap and drawn out of the N to pi star transition band. The shift of the N to pi star transition is not as predictable. For these reasons, empirical Woodward-Fisher rules for conjugated enols are for the higher intensity allow pi to pi star transition. These effects are apparent from the MO diagram for conjugated enols. Aldehydes, esters, and carboxy acids have different base values than ketones. Some examples keep in mind that these are more complex than dienes. UV spectra of aromatic compounds are important. Although aromatic rings are among the most widely studied and observed chromophones, the absorptions that arise from the various electronic transitions are complex. On first inspection, benzene has 6 pi molecular orbitals, 3 filled pi and 3 unfilled pi star orbitals. One would expect there to be 4 possible HOMO to LUMO pi to pi star transitions at observable wavelengths. Due to symmetry concerns and selection rules, the actual transition energy states of benzene are illustrated at the right. The allowed transition epsilon is 47,000 is not in the routine range of the UV observation at 180 nanometers, and is referred to as the primary band E and E1. The forbidden transition epsilon is equal to 7400 is observed if substituent effect shifted to the observation region. This is referred to as the second primary band K or E2. At 260 nanometer is another forbidden transition. Epsilon is equal to 230 nanometers, referred to as the secondary band B. This transition is fleetingly allowed due to the disruption of symmetry by vibrational energy states, and the overlap of which is observed. In what is called fine structure, substitution, oxochromic conjugation, and solvent effects can cause shifts in wavelengths and intensity of aromatic system, similar to dienes and enols. However, these shifts are difficult to predict because the formulation of empirical rules for most part is not efficient. There are several general qualitative observations that can be made by classifying substituent groups. For substituents with unshared electrons, if the group attached to the ring bears n electrons, they can induce a shift in the primary and secondary absorption bands. Non-bonding electrons extend the pi system through resonance, lower the energy of transition from pi to pi star transition. More available n pairs of electrons give greater shift. When substituted with unshared electrons, the presence of n electrons gives the possibility of n to pi star transitions. If this occurs, the electron now removed from G becomes an external electron in the antibonding p star orbitals of the ring. This state is referred as to a charge transfer excited state. When substituted with unshared electrons, pH can change the nature of substituent group. Deprotonation of oxygen gives more available n pairs, lowering transition energy. Protonation of nitrogen eliminates the n pair, raising transition energy. In this lecture, we have learned a lot about instrumentation and spectra of UV. Let's continue in the next class. See you.